where we looked at the normal distribution, where we had a little bit of fun with IQ. And I showed you basically the normal distribution is a typical distribution that is found all the time in nature. And the normal distribution really is, it looks a little bit like a bell. That's why it's also called a bell curve. We have here the mean of the population. And we said this normal curve is symmetrical. And we can put in sort of areas. So this point here would be 1 sigma, this would be 2 sigma, this would be negative 1 sigma, this would be negative 2 sigma, standard deviations. And we said that basically everything that is within the 2 sigma range, or we said everything that is within the 1 sigma range, that is this part here, this contains 68% of our data. And everything that is within the 2 sigma range, that's this red here. How much was that? Can you remember? 95% of the data exactly. So that's 95% of the data. And for example, if we get something that lies in, let me see if I find a nice color. In, oh yeah, that one, that's good. Something that lies in this green area, anything that is larger than this part here, this 2 sigma here, this obviously would be, you can't see it properly, this would be around 2.5%. So if I have a data point that, for example, lies in this region here, there's a 2.5% chance. It's not that I picked that, or 2.5% chance that this is part of this population. It's not impossible, but it's not terribly likely. And what we did last week, or the week before, I had a couple of victims who represented the IQ of certain nations. You remember that? And we said, for example, with this, for the IQ distribution in the UK, IQ in UK, we said we have the population mean equals 100, and we knew that the standard deviation equals 15. And from that we were able to calculate a Z-score, for example. If somebody, let's say, if a nation has an IQ of, let's say, 65, not 6.5, that would a little bit like broccoli. IQ is 65, we can actually calculate how far away this IQ is from the population, from the 100 in a way. And we said we can give that what is called a Z-score, or for our friends across the pond who can't say Z, it is also referred as Z-score, both with a Z like zebra or Zulu in the international alphabet. And we said the Z-score is basically our value for the IQ minus the population mean divided by sigma. Can you quickly do this calculation for me in this case? What do we get? Minus? Minus 2.3. Thank you very much. So we get negative 2.3. What does this negative mean? Negative means they are all dumb. Yeah? Well, in a way it does, because a negative Z-score means it is below the population mean. Positive Z-score would mean it is above the population mean. And when we get negative 2.3, this means basically we are smaller than this 2 sigma range. We are 2.3 sigmas away. So that would be probably somewhere here. Negative 2.3 sigma units away. Now, is it... Good evening. Is it very likely that this person, tribe, nation, or whatever you want to call it, is from this normal population? Is it very likely that we get somebody who has a 65 IQ? Well, we know that everything in this range here, if we just pick that, we would have a 2.5% chance. So it's not very likely to get a person who has an IQ of 65. That is basically what this tells us. Or in other words, if I measured somebody and knew that my population had an IQ of 100 mean and a standard deviation of 15, and I measured somebody and this person had 65 IQ, I could probably argue that they are not a typical representative of the normal population. I could even probably argue that maybe they belong to a different population. Maybe they belong to the group of politicians. No, sorry, I shouldn't say that. They are all very intelligent politicians. Maybe they belong to some aliens who are a little bit, intellectually challenged or something like that. Yeah? So this is basically what this normal distribution can do for us. But there's a slight issue with it, with the normal distribution. What we need for the normal distribution is actually for using normal distribution, we need two things. We need to know our population mean, and we need to know our population standard deviation. And usually what we also need, and we haven't discussed that, the sample that we take the sample size that we operate must be usually larger than 30. There's a sort of a rule of something. If one of these things is not given, so if we don't know the population mean, if we don't know the population standard deviation, or if we have got a sample mean that is, or we have a sample size that is actually smaller than 30, we are screwed. We can't use the normal distribution. Bugger it. So we can go home, right? Ha! Not that quick, unfortunately. Yes. We need to do something else. We need to use something slightly different. And to illustrate that, what we use remember my sister with the lab coat? She phoned me on Sunday, actually to tell me that she has to go to hospital. Apparently she is suffering from, can't remember what it actually is called, but her toes are going in a slightly, bless you, in a slightly different direction. I've heard this is quite common with ladies. Sorry? No, it's more than bunions. It's sort of, there is a sort of a second toe growing or something like that, and it's quite weird. She told me that she has her toes been broken in two places, and then it's been adjusted and things like that. And she got a bit upset because I said to her, "Oh, don't worry, it's it's all fine, it's no problem. Yeah, I know you have to do a general anesthetics and you can't walk for 6 months, but usually we amputate just above the knee, and it will all be good. And I move you around when you have to use a wheelchair and things like that." She wasn't too happy. She used a few very unsavory German expressions on me. And she said, "Oh, by the way, you still owe me an answer to my lab coat problem. You remember? I told you I want to produce these lab coats, and you said you can find out what is the average height so that I can make my lab coats. And when I come out of hospital, I want to start the production of these lab coats. And I said to her, yeah, you see, I asked the students, I measured students, but we had a problem. I did 3 samples of students, and I tried to figure out what is the mean height of the students. And unfortunately, with these 3 samples, I took 3 samples, I got 3 different answers. Can you remember why? Why there were 3 different answers? What was the problem with that? Loud? I heard it? Sample error. Exactly. We have what is known as the sampling error. And she said, you are a complete dep. If you want to look up what dep means, it's not related to Johnny Depp. It's a Bavarian word which is best translated as moron or brain-dead worm or something like that. She said, that doesn't help me. Don't hide behind things like sampling error and big words. I want to know how tall the students are. I said, it's a problem, right? How sure do you want to be, actually? She said, I want to be 100% sure that I get the right measurements. I said to her, oh, if you want to be 100% sure, that's not a problem at all. I said to her, I can tell you with 100% assurance that the students are between 0 and 3 meters in height. And that is the news. She said, you are a depth squared. I said, you asked me, right? I'm 100% sure all the students are between 0 and 3 meters. 100%. She said, that doesn't help me at all. She is difficult. She's really difficult. I said to her, what else do you want me to do? She said, okay, be a little bit less sure, but give me something more tangible. Okay, I said, I can be, so 100% sure, I can be 0.1% sure that the students are all 180 centimeter tall. She said to me, that doesn't help me at all. Because if I make the lab coats 180 centimeters, and you are 0.1% sure, I can only sell 0.1% of my stock. That doesn't help me either. I said to her, what do you want? She said, well, I want you to be reasonably sure that you got the right measurement. And this reasonably sure actually has a name. Reasonably sure means or very sure means is called the confidence level. Very often this confidence level is set to 95%. I want to be 95% sure that something happens. I can't be 100% sure, or being 0.1% sure doesn't make sense either. And 95% is a good value. Or in other words, anything within this 95% is good. Anything outside these 95% is probably not really significant. So, usually a confidence level means we want to be sure about something. I can be 99% sure about something. I can be 50% sure about something. That is what a confidence level basically indicates. And we also very often say, we talk about a significance, bless you, significance level. And that is usually abbreviated with alpha. And alpha and the confidence level are related in that, oh, cool. No, let's carry on. That's nice pictures. Alpha equals 100 minus the confidence level, or 100% minus the confidence level. And I abbreviate that like that. It doesn't mean Champions League. It just means confidence level. So if I have a confidence level of 95%, my alpha would be 100% minus 95% equals 5%. And that is the same as 0.05. Okay. I said to her, okay, Monica, I understand that you are currently under duress, waiting for your operation. So I tell you what, let's see what we can do for you. So I did some more measurements with people in Canterbury, assuming that you guys represent the population of Canterbury. I took 3 samples. Sample 1, height 170, 175, and 180 centimeters. Sample 2, 165, 170, 175 centimeters. And I thought just one for luck. Sample 3, I did 180, 185, and 190 centimeters. Okay, so I've got 3 samples. By the way, can anyone please quickly calculate the average? It's not terribly difficult. What do you get average for sample 1? 175. Sample 2? 170. Sample 3? 185. Thank you very much. So in a way, you see what the sampling error is. The sampling error basically tells me, this is 175, 170, 185. The samples are very clearly, the averages are very clearly different. But they come from the same population, from the population of the good folks at Canterbury. By the way, can you calculate the standard deviation, the sample standard deviation for each one of them? Anyone get any? What did you get? Any starting results? Standard deviation? I can do that in my head if you like. So the first one, the first data point, 170 minus 175 is minus 5 squared is 25. And the last one is 180 is also 5. Squared is 25, so I've got together 25 plus 25 is 50 divided by n minus 1, that's 2. 50 divided by 2 is 25. Square root of 25 is 5. It's the standard deviation. What's the standard deviation for the next one? 5. For the third one? 2015. Okay, 2015. What was your name again? Aha. Is it still 2015? You are 2 years behind.
My name's not 2015.
Yeah, I know. So that's 5 as well. Funny thing, huh? Actually, I made up these numbers, so that's easier for me to do in my head. So each one of these samples has a different mean, but the standard deviation is the same, just by chance. Can you actually calculate the standard error of the mean? Do you remember what that was? I'm going to ask you that in the test. Remember, standard error of the mean. S, standard deviation, divided by the square root of how many data points we have. So this would be 5 divided by square root 3. Or 2.89. Okay? So how does that help us? Well, I want to be 95% sure, 95% confident that I give my sister the right data. So 95% confidence level. And what I can say to her is, where is this 95% here? Can I offer her a range? (95% range). Or in other words, can I, from the data that I got, can I give her a range where I am 95% or reasonably or fairly sure that the data will be in between? And the answer is yes, I can. I can say this 95% range that I'm looking for range of data would be x bar, that's my average of the sample, plus minus what is called the margin of error. Now, what the heck is a margin of error? The margin of error, in a case like that, is actually defined as a factor t, and I come back to that, t times the standard error of the mean. The theory behind it, I don't want to go into it. There are lots of videos on the web. For me, the important thing is that you are comfortable applying this stuff. Yeah? Now, the standard error of the mean, that is this s over square root n. What is this t? There's a long story about this, which I might tell you later. But this t is what I call the fudge factor. This t, this factor, depends on the sample size, depends on n, and the confidence level that I want to use. You can usually look up this t factor, if you know how to do it, in tables, or you can let Excel calculate it. I would not expect you to be able to get this t factor. So whenever there is something where you need to calculate the margin of error, I will give you the t factor. All you need to do is really calculate the standard error of the mean, the SEM, and then multiply it with the t factor. Okay? So that's for tests or exams or something like that. Okay, so what we can do now is we can go back to our table. Here, let me just create a little bit more space. And we can say our margin of error, MOE, would be t times SEM. And in this particular case, the t factor is 4.28. Okay? 4.28. So what I need to do is 4.28 times 2.89, and that gives me what does that give me? Can somebody help me out here, please? 12.36? 36. Okay. So, what does that mean? I can say, for the first sample, sample 1, where the mean was 175. The range of values, and this is actually called, confusingly, the confidence interval. There's too much confidence here. Confidence interval is x bar plus minus 12 point, let's say 4. Let's round it. So that would be was it 162.6 centimeter and 187.4 centimeter. Yeah? So minus 175 minus 12.4. Have I done that right? 162.6? Good. So this is the confidence interval. By the way, this is called the lower bound. This is called the upper bound. So I now can say to my sister, I'm 100% convinced, I'm 100% confident that the height of the students is between 0 and 3 meters. I am 95% sure that the height of the students is actually between 162, somewhere in between 162 and 187 centimeters. Hopefully, this helps her a little bit. Now, I can do that for the other one. I can say, okay, the other sample, that was 182. No, that was, what was it? 170 centimeters. That was sample 2. Plus minus, again, 12.4. That was the margin of error that we calculated. So in this case, for sample 2, the confidence interval would be between 157.6 and 182.4 centimeter. So I can say to her, I'm fairly sure that the height of the students is somewhere between 157.6 and 182.4 centimeters. Pretty sure about that. And for the third, it would be 185 plus minus 12.4. So it would be between 172.6 and 197.4 centimeters. again, I would say I'm pretty sure that the true value for the height of the students is somewhere between 172.6 and 197.4. So let's see. First of all, I said it's between 162 and 184. That's in the first place. In the second place, I said it's between 176 and 182. So it looks like there is a sort of a partial overlap between the two. And in the third place, I said, again, that's this one here, there's again a partial overlap between them. So what I can actually do is, I can plot my data so if I plot here height, and I can draw these margin of errors. And it would look like that. The lower one is always the lower bound. The upper one is always the upper bound. So lower bound, upper bound. And what I see is that there is an overlap between these samples. And actually, the implication of the whole thing is, if I took 100 samples, basically measure 300 people, 100 different samples with a sample size of 3 each, in 95% of the cases, my confidence interval would probably contain the true population mean. But that's a sort of a little bit of hair splitting. Let's not worry about it. We can now draw these confidence intervals. And that is something that I really want you to be confident to do so. Yeah? So I want you to be able to calculate this confidence interval. And actually, there is a sort of a rule of thumb, which I'm incredibly proud to have developed just by doing a little bit of maths myself. You can calculate this margin of error very easily yourself if you have sample size of 3, and that is where very often we do experiments in triplicates. Remember, when you did the assessed practical for the BI 308, you measured in triplicates your absorption of the unknown protein. Remember that? And that's a standard practice in science, that you do triplicates. So sample size is 3, and the confidence level is 95%. And what you then can do is, you take your average plus minus 2.5 times the standard deviation. That's a sort of a simple rule of thumb. This gives you your confidence interval or your margin of error. It only applies to a sample size of 3 and a 95% confidence level. It will change if you have a larger sample size. It will change if you have a different confidence level. But for that standard thing, this works pretty well. Yeah? Make sense? So we just can quickly test this. We said earlier for our measured people, our standard deviation was 5. So we would get x bar plus minus 2.5 times 5, that's 12.5. You calculated 2.3 or something, 2.4 we said, yeah? So 12.5, just by doing that off the top of your head with this rule of thumb equation, is not a bad estimate. It's sort of a shortcut. But it only works for sample size 3 and a confidence level of 95%. Okay? Happy with that? Can you do that? When I ask you to do MOE? MOE? Margin of error? And it's not always 2015. Maybe sometimes it's 2017, yeah, you're absolutely right. Okay, does that make sense? Right, I suggest we have a little break. And then I tell you the story of a biochemist, actually of a chemist, who got the dream job and worked in a brewery. See you in 10, okay?